My name is Cindy DeWitt. I'm Stockholm University. And I'd like to start by thanking my co-authors on this presentation and on the review article that we are preparing on this topic, Derek Muir, Roland Kallenborn, and Katrine Voorkamp. These are the previous webinars covering the main topics of this project on local sources versus long-range transport of contaminants to the Arctic. All of them, except mine now, or all of these at least, are now online on the AMAP YouTube channel. And I've got a link up there for it, but I think Simon has put it in the chat as well. And I'll begin with a short overview to catch everyone up on the main findings, and then I'll present the overarching conclusions and recommendations that we've come to. And just to be clear, which contaminants we're discussing, they include the legacy and new POPs that are listed on the Stockholm Convention for bans or restrictions, and chemicals of emerging Arctic concern. And these are not currently regulated at a global level. In some cases, a few are regulated at national levels or regional levels, but most of them are not regulated. And this list continues to grow as Arctic scientists find new chemicals of emerging Arctic concern in the Arctic. So recent AMAP assessments of persistent organic pollutants, chemicals of emerging Arctic concern, and the effects of climate change indicated that climate change will have effects on the transport and pathways and sources of contaminants, POPs and CEACs in the Arctic. And these include the rising temperatures that will result in loss of sea ice, increased precipitation, glacial melt, coastal erosion, etc., permafrost degradation. But besides long-range transport, there will also be increased secondary emissions. And these are emissions of old POPs and CEACs to some extent, but mostly old POPs that are sequestered in the cryosphere, in ice and snow, in permafrost. And as these melt and thaw, they will release these contaminants to the environment again. But we also have the possibility of increased human activity that is expected with climate change. And this will lead to increases in local emissions of CEACs in particular, with chemicals in consumer products. So in summary, this report indicated that secondary sources of old long-range environmental transport may increase in the future, but that local emissions will also increase. And what was not clear was what impact these would have on overall Arctic contamination, or which of these would be bigger. So based on this, an assessment of local sources versus long-range transport was needed to answer the following major questions. So how important are local sources for total POP CEAC pollution of the Arctic? And do Arctic monitoring data represent long-range environmental transport? This is important. This is an important issue for Indigenous peoples and local communities because it determines how to regulate chemicals they are exposed to from drinking water, food, and air. But it's an important criteria. Long-range environmental transport is an important criterion for listing chemicals on the Stockholm Convention. So we have to know that the monitoring data we are using to show long-range environmental transport to the Arctic is reliable. So there was a need to produce a scientific review of this topic and include climate change impacts, particularly future impacts. And this was carried out with the help of more than 80 Arctic scientists involved. In Katrine Voorkamp's introductory webinar, she gave examples of some of the main open questions that also needed to be answered. Which local sources of POPs and CEACs can we identify in the Arctic? Are specific compounds mainly emitted from local sources? And can we differentiate between local sources and long-range environmental transport in our data? And what are the implications for monitoring strategies and for chemicals management? So the assessment is available as articles published open access in a special issue of Environmental Science Advances. Full references are given at the end of my presentation, but these are the overview articles, the review articles. There are 7, and several of them are already online. And then there are 6 additional case studies, and 5 of these are also online. And there's a link to the special issue there at the bottom. So, what is the state of knowledge? What are our key findings? Increasing numbers of CEACs are reaching or have the potential to reach the Arctic. There are more than 2,200 chemicals in commerce that have persistence, bioaccumulative, and long-range environmental transport properties that could be reaching the Arctic, but have not been looked for. Many CEACs are persistent mobile compounds that are more water-soluble. So we call them PMOCs, and these include PFAS, the perfluorinated compounds, organophosphate esters, pharmaceuticals, personal care products. Microplastics are an emerging issue, including their chemical additives. In a recent report by Wagner et al., they identified 16,000 chemical plastic additives that are used, and of these, 4,200 have persistence, bioaccumulative, and toxic properties or PMOC properties. And thus, microplastics entering into the Arctic may be carrying some of these chemicals. Long-range environmental transport pathways are changing, and this was presented in Haley Hung's webinar. Previously, mainly long-range transport was occurring via the atmosphere. The old POPs, the legacy POPs, and many of the new POPs basically were reaching the Arctic in the atmosphere. This is a fast process and only takes days for chemicals to go from the southerly latitudes up into the Arctic. But now ocean and riverine transport are becoming increasingly important for the CEACs that are mobile compounds and water-soluble compounds. And this is a very slow process and takes decades. So these chemicals will be entering the Arctic for a long time. Here's an example from Haley Hung's webinar. There's a clear concentration gradient from the Pacific to the Arctic for organophosphate esters, and they enter through the Bering Strait. This is similar to an old POP called beta-hexachlorocyclohexane, which several decades ago was found to do the same thing. This is relevant for other chemicals that are more water-soluble, such as the PFAS, pharmaceuticals, and personal care products, microplastics, and microplastic-related chemical additives. Secondary sources are now emerging as an issue. There's evidence of secondary sources showing pulses related to melting cryosphere, such as glaciers, ice, and snow, leading to seasonal pulses. An example of this was given by Christina Koziol in her webinar, showing how PCB concentrations in the summer are higher during the melting season than in the winter melting season. And the concentrations then drop off quickly with distance to the source. A multiplicity of local sources have been documented that release organic contaminants to air, soil, sediments, and water. These are mainly linked to domestic, industrial, and military infrastructure. These include municipal solid waste, where open burning, accidental landfill fires, and inadequate incinerators are located. We have landfills and solid waste sites, both domestic and military, and in these there are leachates and runoff that are occurring, leading to leakage of chemical contaminants into the nearby environment. Fossil fuel burning for heat and electricity generation using diesel and coal, transport also with diesel, gasoline, and other fuels. And for these, many of these sources, PAHs are a major concern to the atmosphere. This makes settlements and towns and also research stations local sources of contaminants, but the levels drop off rapidly with distance from the settlements. Other local sources are mines, onshore and offshore oil and gas extraction, including accidents and spills. Spills can be oil pipelines that break, or it can be oil tankers that leak. Shipping, marine fisheries, and aquaculture are other sources. The contaminants include a range of both POPs and CEACs, including flame retardants, pesticides, lubricants, firefighting chemicals, antifoulants, tire wear particles, and rubber additives, plastics, and microplastics. Airports are sources of PFAS and other chemicals, particularly around the firefighting training sites where firefighting foams containing PFAS have been used or are still used. Fuels and lubricant additives have been found to be sources of some CEACs as well. We have active military sites and decommissioned military sites, such as formerly used defense sites or FUDs, and the air defense early warning sites, or the DEW line. These have, in a lot of cases, waste sites that contain a lot of basically just dumped materials and chemicals, and have been found to be releasing PHs, PCBs, pesticides, flame retardants, PFAS into the local environment. Arctic settlements and towns often lack sewage treatment facilities and release raw sewage or poorly treated wastewater into nearby waters. The wastewater contains many organic contaminants, and these are released to freshwater and seawater. These include pharmaceuticals, PFAS, phthalates, siloxanes, and microplastics. Wildfires are increasing in intensity and in frequency, and they're bringing more smoke and PAHs into the Arctic. We have long-range transport of smoke and PAHs from subarctic and boreal forest fires, but within the Arctic, there are also tundra fires, and these have led to an 8-fold increase in atmospheric benzo(A)-pyrene inputs in a 10-year period, and dioxin and furan emissions in the Arctic have increased due to these increasing tundra fires, to the point where now these are major emission sources during the summer half of the year to the atmosphere. Local fires are also a concern for communities as they have impacts on drinking water if the runoff ends up in the groundwater, and on air quality. We asked for specific examples that are raising concern from Indigenous and local communities as well. In Nunavik, there are higher PFAS levels in people than in southern parts of Canada. The airport is a local source of elevated PFAS to nearby water, to a stream nearby. But the levels in their drinking water, which is taken from another water source, are very low. So this cannot explain the high levels. Instead, food has been found to be the main exposure source. And this means that PFAS contamination here is still from long-range environmental transport and inputs from far away. So therefore, it is still a global issue for them, a Stockholm Convention issue. Regular open burning of waste is an issue in many communities as they are growing and the homes are getting closer to the dumps, and therefore human exposure is increasing. Landfill, in one case, a landfill close to the coast is seeping contaminants into the sea. Drinking water quality, sustainability of supply are issues. There's worry about contamination from glacial meltwater, considering this secondary sources of POPs, for instance, reaching drinking water sources from glaciers. New air defense sites are being built with all the infrastructure around them. There's a new road to Tuktoyaktuk, and this has led to a large increase in traffic in the high Arctic of Canada, and all the traffic-related pollutants that come with that. Mining is also an overall concern in many communities. Future climate change is going to impact local sources of POPs and CEACs in the Arctic. It will lead to an increase in wildfires, which will lead to increases in PAHs and dioxins, possibly other chemicals that we don't know much about because they have not been studied. A melting cryosphere will lead to increase in secondary emissions. Thawing permafrost will also increase secondary emissions of POPs and CACs that have deposited on soils. Coastal erosion will also increase flooding and landslides as the permafrost thaws. Extreme weather events will also impact these. Increased release from thousands of hazardous waste sites on thawing permafrost is expected. And there will be an increase in human economic and infrastructure development. So if we look at human economic and infrastructure development, climate change will lead to expansion of oil and gas production, mining, shipping, cruise ships, fisheries, aquaculture, airports, seaports, and roads. Agriculture will move north. Military sites, we already see an expansion of military sites anyway, but there will be even more expansion. There will be expanding communities as people move from more remote sites, remote villages into the larger communities, and this will lead to increased energy needs and an expanded need for waste and wastewater management. Human activities will also increase the use and emissions of chemicals, particularly CEACs in the Arctic. But we also have to see the positive side. It may also include an increase in green technologies, technological solutions, particularly for the Arctic, better environmental laws, more local governments, and critical community sizes that favor implementation of new techniques such as better wastewater treatment and better solid waste management. Global chemical governance of CACs is generally lacking. Emily Cowan presented this in her webinar. Currently, only 37 POPs are listed on the Stockholm Convention for global restrictions. Global, regional, and national chemicals legislation does not take into account Arctic environmental vulnerability. Regional, national chemical regulations are patchwork. Different countries use different risk assessment methods, and few CACs have undergone risk assessments. National wastewater regulations often are not followed or enforced in Arctic areas of the Arctic countries. So if we now come back to the overarching questions that were posed in this project, what answers do we have and what conclusions can we draw? So how important are local sources for the big picture of Arctic contamination? We've seen a number of examples studying concentration gradients from local sources with distance. So here we have how siloxane concentrations drop off in sediments within 500 meters of a wastewater outfall. In the study of seawater around Ny-Ålesund, higher OPE concentrations are found in water samples in the town area than in the surrounding areas. And the concentrations are lower in the seawater outside the town. The town is a local source to the marine environment, but the concentrations drop off rapidly outside of the town with distance to the source. The research station of Alert is used for monitoring air samples or air concentrations of POPs and CEACs. However, research stations can also be a source of many commercial chemicals, such as the flame retardants. And in a mapping study that Haley Hung also presented, passive air samplers showed that PCB levels were approximately the same and at background levels at the research station as well as at the military base. Whereas for the PBDEs, the concentrations for PBDEs were much higher around the research station, and particularly high outside of the door of one of the research laboratories, but that they fell quite rapidly when they looked at the military site. So again, within a couple of kilometers, the concentrations dropped off very quickly. Studies from Antarctic research stations support the Arctic observations, adding more evidence that local sources do emit various POPs and CEACs, but that the concentrations drop off quickly with distance to background levels that are due only to long-range environmental transport. So here we see the PCB levels drop off very quickly with distance from this research station. Essentially, within 300 meters, they're almost down to zero for many of the different PCB congeners. In the case study by Hude et al. In the special issue of Environmental Science Advances, long-term monitoring data of POPs in ring seals were analyzed statistically based on numerous factors to try to tease out the impact of local sources. These included location, which is a measure of the community population size, the year of sampling, biological factors such as age and sex of the seals, and the presence of local sources and the size of these local sources: mines, power source, airport, military sites, landfills, and wastewater. And the results showed that the local source influence was quite low. So for PCBs, it only explains 17.5% of the contaminant levels in the seals. For PBDs, 3.3%. For organochlorine pesticides, 1.1%, and for PFAS, 0% of the body of the concentrations in the seals. So the results they concluded showed a local source influence that was very low, and the authors concluded that long-range environmental transport is the major source of these contaminants in the seals. So, how important are these local sources for total pollution of the Arctic? Local sources of contaminants in the Arctic form contaminant plumes, but concentrations drop off quickly with distance. Local sources do not explain the widespread occurrence of most POPs and CEACs in the Arctic. Do Arctic monitoring data represent long-range environmental transport? According to us, the authors and the group working with this topic and this assessment, we believe that we think that current long-term monitoring stations are true reflections of Arctic background concentrations. However, to make sure this is the case, site audits need to be done to ensure they are not affected by local contamination plumes. This can be done by implementing passive air and water sampling campaigns near monitoring stations to control for this, and it's important to identify and assess local sources near wildlife monitoring sites. Many CEACs reach the Arctic by both long-range transport and local sources. However, long-range environmental transport is still the most important pathway for most POPs and CEACs. However, we need more studies to tease out the relative contributions of local sources versus long-range environmental transport, similar to the ring seal study by Hude et al. We need studies of riverine long-range environmental transport, particularly for the PMOCs and microplastics. We have old studies of a few legacy POPs showing some of the input from the major Arctic rivers emptying into the Arctic Ocean from Canada and from Russia, but there have been no follow-up studies since really to look for new chemicals and how much is coming from these rivers. So they are major conduits of the water-soluble and particulate-bound sediment-bound chemicals that could be coming into the Arctic Ocean. POPs have mainly reached the Arctic via long-range environmental transport, mostly atmospheric long-range transport, and this is including the secondary sources that now are being released. There are some local sources of POPs. These are mostly related to waste sites. Many chemicals of emerging Arctic concern reach the Arctic both by long-range environmental transport, including in rivers and oceans, ocean currents, and they also have local sources. Pharmaceuticals, however, seem to have mainly local sources. particularly wastewater effluents, but long-range environmental transport may play a role. There is a recent article showing several pharmaceuticals on air particulates at a monitoring station collected from Greenland. Climate change and expansion of economic development and infrastructure may increase the importance of local CEAC emissions in the future. So we need more studies of how long-range environmental transport versus local source impacts will change with increasing human activity. And if this will tip at some point, there may actually come a day when local sources do become important, but we need to have studies that try to tell us if this is the case. There's a lack of data for many CEACs and their sources to and within the Arctic, and this limits our ability to predict current and future releases and emissions. We need more data for more sites in the Arctic to identify other local sources, particularly from the Russian Arctic, where we have almost no data. And even from the parts of the Arctic that were studied, most data is coming from specific communities. There are many communities that have not been looked at, and also many industries. We need to expand monitoring and screening studies to include more CEACs. At the moment, there's a sort of a standard set of chemicals that are being analyzed for, but as I showed at the beginning, there are possibly several thousand CEACs reaching the Arctic that we have not been looking for. We need to determine the bioaccumulation potential and toxicity of the CEACs that are reaching the Arctic. We need measure and modeling studies of CEACs, particularly those related to increased economic activity in the Arctic. Microplastics and their chemical additives are an emerging issue, and we need more studies of these. We need more data for POPs and CEACs in domestic and industrial wastewater. If you remember the last webinar with Pernille Erlend Jensen showed that there were many chemicals that have not been looked for in domestic wastewater, and almost nothing has been looked at in industrial wastewater. More data on POPs and CEACs emitted from commercial activities is also needed, for instance, from mining and from oil and gas production. This information is important for determining which CEACs that should be nominated for possible listing on the Stockholm Convention in the future. Climate change is changing pollutant profiles in the Arctic. There are more wildfires. We have more extreme weather, glacier, and permafrost degradation, and these will increase. We have release of POPs and CEACs from hazardous waste sites on thawing permafrost, and this is predicted to increase. So we have this article by Langer et al. Showing the density of hazardous waste sites around the Arctic that could lead to the release of hazardous contaminants when the permafrost begins to thaw. So there's a need for expanded databases of polluted sites across the Arctic, including the chemicals that are being stored in these waste sites. We need them from domestic and military airport firefighting training sites as well. Only a few airports have been studied for instance, for PFAS. Release of previously accumulated POPs and CEACs from thawing permafrost, melting glaciers, and sea ice will increase. So this is the secondary sources, the stuff that's been deposited and stored in the cryosphere. So we need inventories of the amounts of POPs and CEACs that are stored in permafrost, glaciers, and ice that will be released with thawing and melting to understand how much these secondary sources will release into the environment. And it's interesting that for permafrost, the only chemical we know, group that we know a lot about is PAHs. There's a good inventory of how much PAHs are locked in permafrost that could be released with permafrost thaw, but for no other chemicals. And when it comes to glaciers and ice, we know more about what's being deposited on glaciers and ice than what is being actually released from melting. Solid waste and wastewater management issues are especially important local issues. Many Arctic settlements and towns lack adequate sewage treatment facilities. Effluents release contaminants to freshwater and seawater. Solid waste is openly burned. We have the accidental landfill fires, and many incinerators are inadequate. So we need better solid waste and wastewater management practices in Arctic communities to reduce emissions and to reduce human exposure. We need national quality standards for wastewater emissions in extreme Arctic climate conditions. And the effects of sewage and wastewater emissions on local aquatic ecosystems also need study. Most CEACs in the Arctic fall outside the scope of global, regional, and national regulatory instruments, and Arctic vulnerability is not taken into account. So we need to use the precautionary principle more widely. We may need to explore other instruments, environmental permitting, best available techniques, best environmental practices, mandatory extended producer responsibility, codes of conduct, etc., especially for chemicals that may never fulfill all the criteria for the Stockholm Convention, and for those that are more local problems. We need to develop integrated governance frameworks that address the full life cycle of chemicals and consider Arctic-specific vulnerabilities. And to fully assess future emissions of POPs and CEACs requires greater involvement of Indigenous peoples organizations. So we need to involve them in consultation and engagement in future natural resource and infrastructure development. They need to have meaningful participation in decision-making at all governance levels, and we need greater local community involvement to fully assess local sources of POPs and CEACs, as the people living in the communities know where all of these dumps and hazardous waste sites and so on usually are, actually. So if we go back to the open questions from Katrine Borkamp's intro about which local sources we could identify, which specific compounds come from local sources, if we can differentiate between local sources and long-range transport, and the implications for monitoring strategies and chemicals management. The overall kind of conclusions there are that infrastructure in the Arctic, wastewater and waste handling can be sources of local chemical emissions, but usually with a limited radius around the local source. When it comes to the chemicals, it's mostly pharmaceuticals, but also personal care products and phthalates that have been mainly associated with local sources, generally wastewater effluents. But there are other compounds that can be both from local sources and from long-range environmental transport. When it comes to long-range environmental transport under climate change, we see that the secondary sources are increasing and will continue to increase. But when it comes to local sources, the increases in human activity will likely mean more local emissions. So it's hard to say still which of these might become more important in the future. The purpose of monitoring programs has to be clear. Does it primarily target long-range transport and trying to get a chemical listed on the Stockholm Convention, for instance, or is it about community exposure, integrating different sources such as water, food, and air? So here are the references to the articles in the special issue. You can go back to this and look for these. Several of them have been published since the very first webinar. And with that, I'd like to acknowledge the many Arctic and other scientists involved in writing the review and case study articles. I'd like to acknowledge Indigenous peoples organizations of the circumpolar Arctic and their feedback. I'd like to acknowledge Simon Wilson and the AMAP Secretariat in particular for help with graphics in many of the articles that now are published. Thank you for listening.